OCR A, A-level physics, and this is my second video on circular motion and SHM, and this video is about simple harmonic motion. So, a mass on a spring, in this case bouncing up and down, a pendulum. Now these objects are oscillating freely. We give them an initial displacement and then we let go, and it is a free oscillation. And their displacement from an equilibrium position varies sinusoidally with time. Now, what do I mean by that? Well, their displacement, the equilibrium position for the mass on the spring is there. If the mass wasn't oscillating, it would just be sat there in equilibrium. But we give it an initial displacement, call it x, and we let go and it oscillates, with simple harmonic motion. The pendulum, if the pendulum was in equilibrium, then that is our equilibrium position. So we give it an initial displacement again and we let go and it oscillates. Yes, so the equilibrium position is the center of oscillation. And as I said, the displacement varies sinusoidally. For perfect SHM, it will vary sinusoidally. Now, a mass on a spring and a pendulum, nearly all oscillating objects, whether it's in nature or whether it's man-made, you can simplify it to a mass on a spring or a pendulum. For example, a skyscraper oscillating in the wind is a mass on a spring. A bridge oscillating as people march over it is a mass on a spring. A pendulum in a grandfather clock, a big long clock, there is a pendulum inside which oscillates. I remember as part of my degree we talked about walking, and your legs are what we call an inverted pendulum as you walk along. So nearly all oscillating objects you simplify to a mass on a spring or a pendulum. So this is displacement against time, and I said it is sinusoidal. It's a sine wave. It could be a cosine. I mean, the only difference between a sine wave and a cosine is where you start from. You know, if I started from there, it would be a cosine. Nevertheless, defining some terms, x is the displacement, which is the displacement from the equilibrium position, from the center of oscillation. Capital A is the amplitude, which is the maximum displacement. T is the period, F is the frequency. Some very familiar terms there from, remember when we did waves. The frequency is 1 over the period. Omega is 2 pi over t, or omega equals 2 pi f. Now, what is omega? In circular motion, omega is the angular velocity, isn't it? I would like here not to think of it as the angular velocity. It's just a constant which is related to the frequency. Omega is a constant related to the frequency, and it is measured in radians per second. Okay. It's actually the angular velocity for the auxiliary circle, but not that important. It's just a constant. Omega is a constant related to the frequency. Okay, I said x against time was sinusoidal. So what's the equation for x as a function of time? And if we use these equations, by the way, make sure your calculator is in radian mode. So x equals a sine omega t. As I said, it could be x equals a cos omega t. If you lifted up the mass and then started the watch when you let go, it would be a cosine. But anyway, x equals a sine omega t. A is there because if it wasn't, then the amplitude would just be 1. So we put a in the equation. Omega is there to adjust for the period. Okay, with omega there, which is 2 pi over t, the equation is changed for any period. Okay, not just a period of 2 pi. So x equals a sine omega t. What would a graph of velocity against time look like on the same time axis? So this is displacement against time. Now velocity, remember that v is dx dt. Yes? If you like, v is the gradient. So if you looked at the gradient of this graph, what would the gradient of this graph against time look like? And the answer is, well, if x equals a sine omega t, then v is a omega cos omega t. You can differentiate trig functions, can't you? And as I said, if you look at the gradient, so there it's a positive maximum. So there the velocity is a positive maximum. Here the gradient is 0, so the velocity is 0, etc. This equation v is a omega cos omega t. To work out the velocity, you're given a different equation, and it comes from this auxiliary circle thing and a bit of Pythagoras, and I don't like it, but there it is. V is plus or minus omega times the square root of a squared minus x squared. To work out the velocity at a particular displacement, you use that equation, okay? And from that equation, V max, the maximum velocity, will be when the displacement is 0. Yeah, just the very first point on the graph. If the displacement is 0, then the velocity is a maximum. So we get V max equals omega A. Here's some sums for you to do. Don't be lazy. Pause the video, pen, paper, calculator, do them, and the answers are them. Okay. So we have displacement, we have velocity. The third one we need to worry about is acceleration. So how does acceleration vary with time? And remember that A is dv dt. So acceleration is the rate of change of velocity. So that is the gradient of the velocity graph. So acceleration against time, and there you go. You might actually have to sketch these graphs. I have seen questions where you're given the displacement and you have to sketch the other two. X equals a sine omega t, v equals a omega cos omega t. If we differentiate that, a equals minus a omega squared sine omega t. So we're back to sine, but it's upside down because of the negative, yes, in that equation. What we can do to simplify it is this expression here. We can substitute for a sine omega t, and we get this very important expression, a equals minus omega squared x. Now remember that omega is a constant, so a equals a minus a constant times x. So what's the relationship between acceleration and displacement? They are proportional to each other, but in opposite directions. If one's positive, then the other's negative. Look at this. Consider this mass on a spring. And what we do is we grab hold of the mass and we give it a positive displacement and we let go. What's going to happen? It will accelerate in the opposite direction, and its acceleration will be proportional to its displacement. If we give it a positive displacement, then the resultant force and its acceleration will be negative, and the acceleration will be proportional to the displacement, because for a spring, F equals kx, doesn't it? Yeah. If we give it a negative displacement, then the acceleration will be positive. So the displacement and the acceleration are always in opposite directions and proportional to each other. And that gives us our definition of SHM. An object executes SHM when its acceleration is always directed towards a fixed point and is proportional to its displacement from that point. The fixed point we're talking about is the center of oscillation. Yes, the equilibrium position. All of that blurb as an equation, acceleration is proportional to minus displacement. Compare that with the equation we got on the last slide. A equals minus omega squared x, and omega is a constant. Some sums for you to have a go at using some of these equations. Pause the video, do them, and the answers are, there you go. Okay, last note. Now, for my ideal SHM, for a free oscillation, the amplitude is constant. Okay, now in real life what's going to happen is that for a free oscillation the amplitude is going to get smaller, and it will get smaller. Looking at the graph, it's actually going down exponentially, and that's due to something called damping, and we're going to talk more about that in the next video. So the amplitude gets smaller and smaller, but this is important, the period stays the same. Yeah, we say it is isochronous. The period stays the same. The period does not depend on the amplitude.